All right, so before we jump into the notes, does anybody have any questions that they want to start off with?
Uh, yeah, I do real quick.
Yeah,
Actually, I guess it's in the notes, so I can just wait until it comes up.
that works. And I do want to say we're only going to discuss about 75% of the notes. The stuff with the differing pressures based on height, I'm going to save until Tuesday. So we're going to be talking about buoyant forces and how to calculate pressure at depth.
That's what we're talking about today?
Correct.
Okay, that was my question.
And then I'm going to give you guys practice problems at the end that are AP style and should give you a good idea of what types of test questions you can start to expect. Why is this not updated? There it is. All right. What's that, Gabriel?
There's a problem that has and it has the mercury and the water in it.
Yes.
You recall it?
We are going to discuss that on Tuesday.
Okay, because honestly, a lot of the practice problems I rarely got. Like, I understood the reading, but it was hard to put it into the actual, equation.
Yeah, and the problem with this unit, at least with how it was written in the text, is it felt really jumpy. Like it would discuss this, which works with this, but then it sandwiched this in the middle. So I pulled those differing pressures like the barometer, and that's going to be our discussion on Tuesday. That being said, I think the way that the text words things and phrases things is fabulous, and I think it makes more sense. So I am going to try to continue using it. I will do a better job, or at least I will try to do a better job, checking the material for mistakes beforehand. And we will go over the couple of mistakes that I found, or that rather students found, as we go through it today.
Go ahead, sorry.
No, go ahead.
Yeah, no, go ahead.
Well, I thought I'd
Gabriel.
Huh?
It's fine.
Huh?
What did you
Fine,
say?
Gabriel, you can go first.
Said it was fine for me to go, I think. With the delay, it's always like you're interrupting somebody else as soon as they try and say something. So you said we were going to do buoyancy and how there was an object suspended in a fluid.
Correct.
Okay.
And who else had a question?
What textbook are you using?
The 5 Steps to a 5.
Wow, I like the sound of that.
Is that not the homework assignment that you did?
No, that's the one I did. It's just I remember last year we used like the Princeton textbook or.
We will also use the Princeton review book, but I think this book is best for introduction and getting started with it.
Also, I did all my notes like all at once, so I turned it into notes 2, but like it has my notes 1 in it.
That's great.
So do you want me to? Okay, I was gonna say, do you want me to separate it and like
Nope.
half and half it? Okay, thank you.
Yep. As long as you turn it into both assignments.
Okay.
All right. So first, some people had questions on the bouncing nanoparticles. I just want to kind of go through that. There's a lot of particles bouncing in a contained object. Some will bounce in from the bottom, which will push it up and out. Some will bounce in from the top, which will push it down and out. On average, with as many collisions as there are in a container, the upward ones are going to balance out the downward ones. So they can be ignored, but nothing is balancing the outward forces. So all that diagram, that paragraph was saying, was that in a container, the average or the only unbalanced force on a container is outward, which is why the box or the container of fluid doesn't automatically shift to the left or shift to the right. It just gets pressed outwards.
That makes so much more sense.
Yeah, it actually took me 2 read-throughs and a student asking me about it for me to understand what they were saying. And the student got it right, and I was wrong with my initial interpretation of what they were saying.
Could you just repeat that again, just the way you summed it up?
Yes. So you see how particle A on the bottom bounces up?
Okay.
When it does that, it's going to push the wall upwards, but it's also going to push the wall outwards. And when particle B at the top comes in, it's going to push it in this direction, which means it's pushing it down a little bit, and it's pushing it left a little bit. So the downward force of the one particle and the upward force of the other particle, because there's always collisions, there's going to be an average number down and an average number up. They should balance each other out. So the only forces that aren't balanced are the outward forces, because there aren't particles from the fluid on the outside pushing it back in.
So,
The big takeaway I want you to get from that is that in a fluid-filled container, there's pressure pushing on the surfaces always outward. And I guess not necessarily always outward, but outward from the fluid. So if you have a submerged object, even though they're pushing outward on the walls of the container, they are pushing inward on the surface submerged.
So I have a question.
Yeah.
So how come the forces on like perpendicular to the wall are unbalanced? Is it because that energy is then like what's hitting against the wall is then getting reflected back and then like that's the
Okay, that's a really good question. I'm going to have particle
Direct
A come
action
in this way.
force? Or I don't get why they don't cancel out. So,
Absolutely. Let's have two particles, particle A and particle B. Particle A is going to push the wall this way, right? Which means it's going to push it outward, and it's going to push it downward. You can think of this diagonal force as two different forces, a horizontal force and a vertical force.
Kinematics.
Yeah. Are you guys with me up to this point about how we can break that diagonal down left into a leftward force and a downward force?
yeah.
yes.
Yep.
Similarly, when particle B comes up, it's going to create a leftward force and an upward force. Still with me?
Just
Yes.
So now once you get to that point, this upward force is going to cancel with this downward force. That's going to happen on average to completely balance out, because there's particles coming down, there's particles going up, but the downward ones are going to balance out the upward ones. But nothing is canceling out the leftward forces because there's no water molecules outside pushing in on it. Better? Or still no?
No, that makes a lot more sense.
Okay.
So, would this only happen if two molecules were hitting the wall at the same time? Like two or more? Or would it happen also when there's just one?
If there was just one, it would eventually bounce around enough that it would push downward, bounce around a couple of times, and then bounce upward. So on average, over a tremendous period of time, one molecule would balance itself out. That being said, to have one molecule of a fluid, a gas, a liquid, whatever it is, in there, I guess it would have to be a gas for it to be bouncing around if there's only one in there. But to have only one molecule in there would be basically a
Insane.
vacuum, and the pressure on the outside would crush the container.
Well, no, I don't mean that there's only one in there. I mean, there could be multiple molecules, but only one at a certain period of time hits that wall.
Oh, okay. So because there's not 10 molecules in there, because there's millions of molecules in there, there's so many collisions on every wall all the time. Think about air molecules hitting your arm, 1 square inch on your arm. So let's take this square inch. For one molecule to hit your arm would exert so little force and so little pressure that it would basically be absolutely nothing, right?
Like it'd be not.
It would basically be a non-existent force, a non-existent pressure. Would you agree with that statement?
Oh, go ahead.
Do you agree with that statement?
Yeah, so like for it even to be a concern, there would have to be multiple molecules hitting at the same time.
Right. We're talking about millions of collisions constantly.
Yeah, okay.
And with millions of collisions constantly, you can make a very safe assumption that half of them are up and half of them are downward because you've gotten rid of a rare situation where the molecules are mostly going up or mostly going down. With that many collisions, on average, half would be up and half would be down.
Yeah, okay, that makes a whole...
Okay.
Thank you.
You're welcome. All right. So a very simple, straightforward question. We have a beaker that is open to the atmosphere with 2 heights in the fluid. We have height A and height B. Where is the pressure greater and why is the pressure greater, at A or B?
I would say B
Because why?
the molecules would be more packed together at the bottom of the.
Good. So if you're looking at if you put an underwater scale at A, that scale would only have to support this much weight of water. But if you put the same scale at B, it would have to support this much and this much. So the pressure at B has to be more, which if you've ever swum to the deep end of a pool, you've felt. The deeper you go, the more pressure you feel. It has nothing to do with how wide the pool is. The only thing that matters is how deep you are.
And you can take the Mariana Trench, and they've been trying to get submarines down there for years, but the pressure that's all the way down there, it's the deepest, what you call it, trench, underwater trench in the world.
Mariana Trench.
Pressure so intense, everything just gets crushed.
That's exactly it, Garrett. That's exactly it. Good.
So, real quick, is it cool if I ask a question?
Please, I want all of you guys to ask questions.
Okay. So there were some notes talking about like the shapes of containers. So how come if it's like a conical shape, wouldn't at the bottom there be more water supported by those few molecules?
That's a really good question. All right, so I have a water level that's equal to the water level in this cone. The height is the same, but I think what Drew's suggesting is this surface A, has to support this amount of water. And if we take a similar cross-section in B, what about this extra water? Why does that not also weigh down or add more pressure to location B? Is that what you're asking?
Yep.
Would somebody in here like to take a stab at that?
I guess. Well, I would say because since it's like a cone, the water that's hitting against the edge is also sharing the pressure on the back of the edge instead of going straight.
Wait, I lost you at the end.
So it would put more pressure onto the sides of the
I'm assuming this is a cup, right? Yeah, so it would put more pressure on the sides of the cup than onto the bottom because it's not straight.
Correct.
Because of adhesion.
B only has to support the area above B. This water molecule isn't pushing on the surface at B, it's always pushing downward. So this spot has to support this column of water. And this spot supports this column of water.
So it's only pushing directly down.
Correct.
Like straight,
Yes.
straight line down. Okay.
Okay. So
Makes a lot
let's say
more
sorry. Let's say I had a cone cup, except instead of being with the pointy end down, I had like the wide end at the bottom. On
Flask.
Yeah, sort of like that. And I filled it all the way to the top. On like the edges, there would be less pressure at the bottom, right?
Correct. Because there's less height above it. Wait. I want to make sure. I might be misunderstanding you. So let's say this is your object and it's open to Earth's atmosphere. And then your water is here. You're saying over here?
Yes, that's what I'm saying.
No. Okay, so that still is this height below the bottom. So even though it looks like it only supports this column, and that's how I phrased it, these water molecules are still more densely packed together because these push down, which push these ones further left and right. So even though the particles in the middle or off in the top left corner aren't pushing down on B, they still densely pack the water together further towards the bottom, which means it supports more weight.
So what you're trying to say is in that tiny column there in the corner, there's a higher concentration of water molecules than what
That's exactly
top
it.
was. So
That's
even
exactly
though it's
it.
like looks tiny, there's like more.
Yes.
There's more, yeah.
So regardless of the shape, think about it as blankets of water. So if you're at height A, you have to support 1, 2, 3, 4, 5 blankets of water. At height B, you have to support 4. At 3, you have to support 2. At 2, you have to support 1. And 1, you only have to support the weight of atmospheric pressure, P naught. By the way, I'm going to say that a lot. Not N-A-U-G-H-T. That's how we say 0. So pressure 0 or atmospheric pressure, I'm probably going to say P naught.
I thought that meant beginning.
Huh?
I thought that meant like your starting pressure.
And it also means starting. Yeah, we use that like with initial velocity, your starting velocity, we did V naught because that's your velocity at time 0. That's your pressure at height 0.
100,000 pascals.
Which is equal to 100,000 pascals at Earth's surface.
Why did we have to choose like such a small unit of measurement?
I don't know, man. It's ridiculous. They insist. Oh, it's because we need everything to agree with each other. So we need to use kilograms.
Okay.
We need to use newtons. We need to use meters. And if you take a newton divided by a square meter, it's a really, really, really small weight. It's the weight of a small apple spread out over a square 3-foot surface.
I know, but like instead of saying 100,000 pascals, why couldn't we just say like 100 kilopascals or something?
I mean, you can do that, but when you plug it into your calculator, make sure you convert it back to pascals.
That's true. See, craziness.
Heck, you could even call it 1 atmosphere if you prefer, or 15 pounds per square inch if you prefer, as long as when you plug it in, you change it back to 100,000 pascals.
Yeah, but they were like grams are too small, so we're going to change the standard to kilograms, but we can't do that with pascals at 100,000?
That's because pascals have kilograms already baked into them. So now you're going to have kilograms, which means you're breaking newtons.
Megagrams.
Megagrams, yes.
Yes.
Good?
Yeah.
Grams.
All right, so now the density equation. What is density in your own words? Anybody?
How much stuff is in a thing?
Good. I like that. How much stuff is packed into a specific area? How much mass, how many particles is packed into a volume? So this equation should make complete sense to you. You do not have to memorize this equation. It's the first equation on your equation sheet. So you don't have to memorize it, but when you look at it, it should be like, yeah, that makes complete sense to me. I logically understand why density is mass divided by volume. What would the units for it be?
Grams. Oh, would it be kilograms per cubic meter? Isn't that what we're using?
Right, since it's mass over volume, and by the way, for volume we use capital V, because lowercase v we already use for velocity. So m over capital V, mass over volume. Mass is measured in kilograms, and volume is measured in cubic meters. So your density should be in kilograms per cubic meter. Does anybody remember the density of water?
1,000 kilograms per cubic meter.
Good. Density of water is 1,000 kilograms for every cubic meter. Means if you have a cube of water, it's going to have a mass of 1,000 kilograms.
That's heavy.
That is heavy. Water's exceedingly heavy. All right. And the other thing I want you guys to start paying attention to is make sure you can rearrange your equations. So if you have density equals mass over volume, and I wanted you to solve for the mass, could you do that? How would you get mass on its own?
Multiply both sides by mass.
Multiply both sides by mass. So if I have density equals mass over volume, if we multiply both sides by mass, you're going to get, on the left side of the equation, mass times density equals mass times mass, or mass squared over volume. So it's not multiply by mass.
Multiply by volume.
Multiply by volume. So we multiply both sides by volume. And now look at the right side of the equation. Volume in the numerator, volume in the denominator. They will cancel each other out. And especially in the beginning, I will try to work through how to algebraically solve these problems. But volume in the numerator and the denominator, they should cancel each other out. And you're left with mass equals density times volume. So the more you get to play around with these equations, the better you will be with them. Good?
Yeah, this is starting to make some sense.
Good. Yeah, and that was the other thing I wanted to say to you guys. If you were taking the notes, and you were like, holy crap, what have I signed up for? This is really overwhelming. The beginning of every unit is going to feel like this. I think my students from last year can probably attest to that. The beginning of every unit is scary. The beginning of every unit is a new language. The beginning of every unit is something you haven't done before. And it will be hard. And then by the end of the unit, hopefully it will feel like, okay, I get it now, and that's a cool feeling. And then 2 days later, you start a new unit, and it's awful again.
I don't know, it depends, because some of the units, a lot of it translates over.
Yeah, that was very true last year. This year, our units are much more compartmentalized.
Yeah, I heard that from one Mr. William Meyer.
Yeah. Which I like. It gives you a fresh start, but that also means you're starting over every unit.
He said this was his favorite class.
Really?
This one specifically. He said he liked 2 far more than 1.
I do too. I'm excited for this year.
So am I.
Get it? I do too.
Cool. All right. So now, pressure on a surface. We've already discussed a bunch of
quick
these.
question.
Yeah.
Just so I can kind of visualize it, how big is a meter cubed?
You remember my meter sticks from class? 3 feet long?
Yeah.
It's one of those by one of those by one of those. So it's a cube with one of those on every side.
And that's 1,000 kilograms of water?
Yes.
Well, water's
right.
actual density is 1 gram per centimeter cubed.
Which is the exact same as 1,000 kilograms per cubic meter. If you did the math, it would be the same thing.
Yeah.
So
It's
if
just
you have a
whatever
cubic
big-
centimeter, which is about your smallest knuckle, so if you have a cube like that, or I guess the width of your finger would be a better centimeter. Width of your centimeter, really the tip of my finger is a cubic centimeter. That would have the mass of about a paperclip, which doesn't seem like much, but when you think about 1,000 kilograms in a cubic meter, it's like, holy crap, water adds up quickly.
Now you think
Yeah,
of
that's
something
insane.
Like
Yeah.
gold or like tungsten, which is like 19 per cubic centimeter.
Are you serious?
I think it's something like that.
That's absurd.
That would be like just too heavy.
Yes. All right, so now we've already discussed pressure is measured in pascals, and 1 pascal is 1 Newton per square meter. And I did some math to figure out what that would be like in terms that would make more sense. That's the weight of about 9 paper clips spread out over a square foot, aka not a lot of pressure. So the weight of air, I guess, would be 900,000 paper clips over a square foot, or 1 million paper clips on a square foot, which feels like a lot because it is a lot.
But we adapted to it perfectly.
Yes. You don't forget a letter that I say.
Oh no.
All right. So now to calculate pressure, and this equation is also on your equation sheet, but we will discuss it so it makes sense. Pressure is how sharp a force is, or rather, how much force is packed into an area. So,
I remember exactly. You did the book. You had the book. I have a picture of you pressing it into someone's head with a devilish grin on your face.
yes.
But
So I have 4 pounds of force spread out over 6 square inches, and it doesn't hurt a lot. But if I take that same 4 pounds of force and put it over a small area, holy smokes, it hurts like the dickens. That's
That was
exactly it.
bad.
Huh? Now,
Do we need to?
what?
Yes, Andrew.
That was my head, or at least one of them was.
Really?
Yeah.
That's awesome.
I'll go back and I'll find it and I'll put it in the Discord.
I would.
Eric gets
Yeah.
very excited whenever pressure units are involved.
Pressure's my favorite. I love pressure. Light's my favorite, but pressure I think is number 2. They're
Well,
both
you
up
didn't
there.
You didn't teach
Is it
light.
pushing down on you?
Yes. Now, could you rearrange this pressure equation for force? How would you rearrange
Yeah.
this pressure equation? What would you have to do to get force on its own?
Multiply by area.
Multiply both sides by area, since area is in the denominator, so that it can cancel out. And whatever you do to one side, you have to do to the other. And then you get the equation FAP, which should be a super easy equation for you guys to remember because we discuss forces in AP. Right? Force in AP.
I don't don't know
Yeah,
if that's
FAP, I like
why.
that one.
I don't know what you people are talking about. So another thing to be really careful of in this unit is that area. Most of these things deal with circles and cylinders and pipes. So what is the equation for area of a circle, cylinder, or pipe?
Pi r
Cylinder-
squared.
It's pi times the radius squared. So you have to be super careful. A lot of times they'll tell you this pipe has 4 inches in diameter. In that case, you would have to make sure that you convert it to the radius and divide it by 2. 2 inches. Questions? Okay. Gauges. This problem gave us probably 2 weeks of fits where we couldn't figure out why we were always off by 100,000 pascals when we were working through problems. Could
funny.
not figure it out. But your total pressure, and that's what absolute pressure also means. It's the same as total pressure. Your total pressure is equal to what the gauge will read plus 100,000 pascals, which makes sense because if you hold a pressure gauge in your hand, what does it read?
1 atmosphere.
It doesn't.
Reads nothing.
It reads 0. But the pressure pushing in on the gauge isn't equal to 0. How many pascals are pushing on the gauge?
100,000.
100,000. So if you want to know the total pressure and your pressure gauge reads 40,000 pascals, what is the actual pressure of the fluid that you are measuring?
140,000.
Yes. So it's the gauge pressure, which in this case was 40,000 pascals, plus atmospheric pressure, 100,000 pascals. And thank you, I think it was CJ for catching that. So the total pressure in that
Thank you,
case would
CJ.
be, what?
I said thank you, CJ.
Yeah, thank you, CJ. That's a huge catch, and I might have just glossed through it. I probably would have. I think I did. So the total pressure would be what the gauge reads plus the atmospheric pressure that's also pressing on it. Assuming, that's a very big assumption, assuming that the fluid is in fact open to the surface, meaning there is atmospheric pressure pushing down on the water. So then it would have P naught plus the other pressure. But gauges always read 100,000 less than atmospheric pressure if you're at Earth's surface. All right. So now my question, what is the pressure at the surface of this beaker?
Uh, 100,000 pascals.
Good. How did you know that?
Isn't that the air pressure we generally use in physics?
It is, but you knew that it was 100,000 here because it is an open container, meaning it is exposed to Earth's atmosphere. Cool?
Yep.
Okay, good. How could this pressure at the surface possibly be different than 100,000 pascals?
If it was inside a vacuum.
Good. If this was not exposed to Earth's atmosphere and you added more air into it or removed air from it, it would be more or less than 100,000 pascals. So when you look at a problem with this, it's always a good idea to think, is it exposed to atmospheric air or is there a different pressure on the inside? All right, so now that we've figured out the pressure at the surface, which I'm going to call P naught, how does the pressure at A compare to the surface? In the simplest terms you can give me.
more pressure at A than at the surface.
Good. So pressure at A is greater than the pressure at the surface, P naught.
How can you tell the difference?
The difference of what?
Well, like, how you know how much pressure is already going into it by looking at a diagram.
Oh, okay. So
That's
if
lost me because you had two people reading it like they just knew it like that, and I'm like, how do you know that?
okay, so at the surface, is it exposed to open air?
Okay, yeah, I got that part.
So that means at the surface it's equal to 100,000 pascals from the air pushing down on it. But then when you go down to A, you know that it has the weight of the air pushing on this top surface, and then you also have blankets of water pushing down on A. So you have the weight of the air above it plus the blanket of water between A and the surface.
Okay.
So basically, the deeper it is, the more pressure you have. Better?
Kind of. I'm just like, wondering where they pulling some of these numbers out.
Oh, the 100,000, that's the only number we have. That's pressure at Earth's surface.
I'm just a bit slow with this, so.
It's what?
I'm just a bit slow with this.
No, you're fine, man. This is the first day we're discussing this. And again, that's why I'm recording the video so you can go back and watch it if you get into problems and it doesn't make sense again. Because you might get through these notes and be like, yeah, I got everything we were discussing today. And you still might get lost. Or you might come out of this and say, what the hell did we do? Go back and watch the video.
Wait, there's a video?
I uploaded the video from the first notes. I'm
yeah,
currently
there's
recording a video for these notes so I can get them uploaded by the time I go home today. That's my ultimate goal.
Just letting you know, the document from the Surface Bear Notes, I downloaded it. There was no handwriting whatsoever.
There was no handwriting.
I didn't see any.
Okay,
Yeah, there
then
wasn't.
I will re-upload that. Thank you so much for letting me know.
The original that you had uploaded at like 11,
Yeah.
whenever I brought it up to you, that one had your writing on it. So I don't know why it went away or how it went away, but
Okay, then I will re-upload that. Thank you guys for letting me know.
Yep.
That's huge. All right. How does the pressure at B compare to A? Garrett, I'm going to ask you to take a stab at that, man. How does the pressure at location B compare to at pressure A?
Probably more pressure because it's deeper, so.
That's it?
Yeah.
That's it, man. Pressure at B is greater than the pressure at A. Good. All right. So now we get to the equation to calculate the pressure at any depth in a fluid. And your total pressure, your absolute pressure, is equal to the pressure at the surface plus rho GH, or the density of the fluid times gravity times your depth below the surface. And there is a key to the right to help you out with that. One thing to note, which they pointed out here, is the initial pressure, P naught, is not necessarily going to be 100,000. Like we discussed before, it might not be exposed to open air. It might be slightly less than 100,000. It might be slightly more than 100,000. And to get from this equation, equation 1 to equation 2, they just brought P naught to this side. So the pressure minus P naught equals rho GH. Or rather, the difference in those pressures, the change in pressure, the delta pressure, that's what that Greek letter delta means. It means the difference between the two is equal to rho GH. You don't have to remember this. That doesn't matter at all because this equation will always get you to the answer.
First one.
The first one.
And even if you do use the second one, half the time you expand it afterwards.
Absolutely.
Because that's like using that one equation in kinematics. When we would put delta x or delta y, I would always expand it afterwards.
I did too, man. And honestly, if I were thinking about everything I wanted to say, I probably would have cut off the bottom of this image so that it wouldn't even include that equation.
Yeah, that's just if you want to save space.
Yep.
Have your base equation down.
Yeah, that's exactly it. You're good. All right, so now we're going to write a pressure equation for A compared to the surface. So what is the pressure at A compared to the surface? Or rather, just what is the pressure at A in terms of the density of the water, the height from A, and I'm going to say height sub A is the height difference between A and the surface of the water. Atmospheric pressure and universal constants. And whenever you see universal constants, right now that pretty much means gravity. So does anybody want to take a stab at the pressure at A in terms of these variables?
I can if you want.
Yeah, go ahead, Drew.
The pressure at A is equal to P naught of the atmosphere plus the density of the water multiplied by gravity multiplied by height sub A.
Good. And that equation came from the same equation I told you guys before. The total pressure, the absolute pressure, equals P naught, or the pressure at the surface, plus rho GH. And one thing I want you to be really careful about in this equation. The density is the density of the fluid. That is crucial. It's not the density of the object, it's the density of the fluid. So the density of water times gravity times the height below the surface, which is H sub A. Good?
Hold on.
All right. So now I want you guys to take a second and try to write a pressure equation for B, assuming that HA is still the same as before. HA is the difference between A and B, and HB is from A down to B. So this one's a little bit more involved. It's just one more step to work through. See if you can write the pressure equation. And again, I always encourage you guys to start with your base equation.
So we're comparing B to A.
You're comparing B to A.
That's the next one, Mr. Barrett.
Oh, B compared to the surface. B compared to the surface. Thank you for catching that. One, two, three. Okay. Whew. I think we're gonna make it.
No offense, Bear, but when does this class, what time is this class scheduled to end?
1:15.
Okay, that's what I thought. Halguda sent me a calendar invite for my Impact to Technology class for 1:15. I was like, that sounds kind of early.
Yeah, I screwed up my schedule yesterday. I thought it got out at 1 o'clock, so I dismissed all of my students 15 minutes early. And I was rushing to get done by the 15 minutes early. I couldn't figure out why I lost 15 minutes in class until after class ended.
That's all good, Bear. This is a learning process. We're
It
still
is.
trying to figure it out.
Olin, why are you discussing fantasy football in Discord during class? All right. Who wants to walk me through what they got for this? Somebody new want to jump in? No? Does anybody want to jump in?
I can, if you want.
Go ahead.
Alright. The pressure at B equals to the atmospheric pressure plus the density of water times gravity multiplied by HA plus HB in parentheses.
Good. This, I think, is why this problem was tricky. Because the height down to B, the depth at B, is equal to the height to A plus the height from A to B. So the total height, the total depth below the surface is HA plus HB. So we substituted that in for the total height. Good. All right, if you didn't get that, here's your chance for redemption. And I'm actually going to change this variable to pressure at A. So write a pressure equation for the pressure at B compared to A. So how does pressure at B compare to the pressure at A using the density of water, the height at A, the height of B, and the pressure at A, which we already calculated? All right, I'm sorry. I am going to cut you guys off because I want to make sure we get through this before the end of class so I can talk about how I want you guys to do the homework. Was anybody able to get the pressure for B in that short amount of time?
I mean, I took a guess.
Please, give it to me.
Pressure of A plus the density of water times gravity times the height of B minus the height of A.
I slightly disagree.
Okay, that's fine.
You're close. You are really
what
close.
I thought was best.
No, you were super close. Anybody else?
Is it height of A minus height of B?
It's not height of A minus height of B. Good guess, though.
Is it just height B by itself?
It's a very fragile thing.
It is just height of B by itself because we already have the pressure at A. So we already have the pressure at A, and now we just have to add the extra pressure from A to B, which is density of water times gravity times the height difference between A and B.
And didn't we define height B as the difference between A and B beforehand?
We did define height B as between A and B.
Yeah, that's why.
That was a tricky problem, so if you didn't get that, please don't be discouraged.
So wait, real quick.
Yeah.
I just want to clarify what that was actually asking me. Was it asking to find the pressure at B in terms of A?
In terms of A. I probably should have
okay.
rephrased that. In terms of. I'm sorry. Yeah, it was a poorly worded question. I would agree with that.
But also, doesn't it say we have to use the height A and height B in our equation?
No, just because the variable is offered does not mean you are required to use it.
I'll bury you in your red herrings.
Red herrings. They will show up a lot. And I'm trying to get you guys used to realizing you don't have to use everything you're given. All right.
So
I'm going to pause you guys for 1 second. I'll take more questions in a second. But
Okay.
I want to say while we have 2 minutes left, because some of you guys probably do have to go at 1:15 on the minute. You do have a homework assignment that is 16 multiple choice questions. The answers to those 16 questions are at the bottom of the assignment. They are due on Tuesday. For multiple choice questions, I don't care if you get them right or wrong. I care that you try to explain or justify your answer for every one of them. So with every question you do, you have to make an attempt to justify your answer. And instructions for that, I do have it written out in Schoology, but I wanted to say it out loud while I have all of your captive attention.
So by defend our point, you mean just show our work, or do we have to write also why we think it's like that?
So if it's a calculation, showing your work counts as a justification. If it's a conceptual question, you need to tell me what conceptually made you choose the answer you chose.
Okay.
When's it due again?
It's due Tuesday.
Okay.
Are we gonna start back on these notes Tuesday or?
It depends on how many questions we have to go over on Tuesday. So on Tuesday, we're going to go over the questions that you guys want to go over first. And then after that, we'll jump back into the notes.
Okay.
That's our order. I don't know when we'll finish one and start the next. It depends on how many questions you guys have.
I'm going to be honest. I don't understand what you meant by conceptual question.
So if they say, why is the pressure greater at B than at A? And then it's a multiple choice. Let's say one of the answer choices is there's more molecules of water on top of it. You would say, I know that the pressure is greater because there's more molecules on top of it. That's a terrible example, but I think when you look at the questions, it will make more sense.
Yeah. Okay. All right. Thank you.
You're welcome. And it is 1:15, so if you guys have to go, you are free to go. I'm just going to quickly go over the density or the buoyant force equation, which is just density is buoyant force is rho VG. And I'm also going to go over how to calculate
later,
this.
Bear. I gotta go. I'll watch your video.
Okay.
Yeah.
Yeah, if you guys have to go, go, but I'm going to go over this if anybody is still around. Have a good day, guys. Thank you for coming out.
Thank you.
Thank you. Oh, you just logged in. That's why you're waving. I get it now. Cool.
The
All right.
party has arrived.
We've gone through most of the notes, and now we have 2 slides left to go over. And the video is recording, assuming nothing went wrong. My audio's not screwed up, and I don't have to re-record it, which I'm praying I don't have to do. That would be wonderful. All right, so now we're going to recap buoyant force. And your equation for that is buoyant force is equal to density of the fluid times the volume submerged times gravity. There's 2 really important things with this equation. Number 1, density of the fluid. I don't care what the density of the object is. I care about the density of the fluid because the more molecules you have in here, the more they're going to push up and support its weight. And similarly, the other thing is not the total volume of the object, but it's only the volume submerged, which makes sense because if you have a milk carton and you jam it underwater, the more volume submerged, the harder it is to push up or to push down further because there's more buoyant force supporting it. And I'm sure you guys have all tried to shove something underwater and felt that. So that's your buoyant force equation. Now, this is a recap of the problem we worked through in class last time. We have a mass hanging from a rope submerged in water. and a spring scale that reads 5 newtons. So I'm going to put my spring scale right here. The force of the spring equals 5 newtons. But when it's, I'm sorry, let me redo that. I got that backwards. When it's hanging freely in air, it reads 5 newtons. But when you hang it in the water, it reads 4.2 newtons. What is the density of the object in this problem? And I want to kind of walk you guys through my thought process so you can kind of see how I approach these problems. Number one, I want to find the density of the object. So to do that, I need an equation that has density in it. And the first one that pops to mind is mass and volume. So if I can find the mass of the object and the volume of the object, I'm set. Those are the two things we need to solve for the density of the object. So now I need to figure out, okay, well, what's the mass of the object? I have no idea off the top of my head. But that's when I go back and look at the problem. And when you're working through problems, it's always a good idea to underline key things that you want to read. 5 newtons when it's hanging from there. How can I use that? And 4.2 newtons when it's hanging in the water. So once I have a diagram, I start looking at it and I think, okay, now I'm stuck, but I at least can create a net force equation for both of these force diagrams. Are you guys with me up to this point?
Yeah.
Okay. So what forces are acting on it when it's hanging from the spring in air?
Gravity down and then tension force up.
Gravity down and tension or spring force up. I don't care what you call it. I'm going to call it spring force just because that makes sense to me. And we know that that spring force is 5 newtons because that's what the spring scale reads. Gravity, we don't know. But we do know it's equal to, does anybody remember the equation for it? For the weight of an object. Mass times gravity.
Yeah.
And the more you guys
Yeah.
work with that equation, the more that equation is going to become second nature to you. So now I still feel stuck, but whenever you're approaching these problems, start with a free body diagram, and then if you're still stuck, make a net force equation. Net force is mass times acceleration. What's our next step once we have a net force equation?
Fill in what forces are acting on
Good.
it on the left side.
Really good. Spring force is up, so it's positive, and force of gravity is downward, so it's negative. So we have the spring force up minus the force of gravity equals mass times acceleration. And then I keep filling things in as I go. What can we replace force of gravity with?
Mass times gravity.
Good. And hopefully that will spit out what the mass of the object is. But what about the right side of the equation? We still don't know mass. Do we know the acceleration?
There isn't any.
Oh. Yeah.
Why is the
There's no
acceleration 0?
Because it's not going faster or slower and it's not changing direction.
Beautiful. So the right side of the equation is going to collapse to 0. So now we know 5 newtons equals mass times gravity if we bring this mass times gravity to the right side of the equation. I skipped a step. I shouldn't do that. 5 newtons minus mg equals 0. So now we can bring this to the right side of the equation. And we know 5 newtons equals mass times gravity. But how do we get mass on its own?
Divide by gravity.
Divide by gravity. What is gravity?
10
10
meters per
meters.
second per second.
Good. 10 meters per second per second. And 5 divided by 10 is going to give us 0.5 kilograms. Holy smokes, we have the mass. which means we have half of the things we need to solve this problem. So how do we find the volume? Again, go through that same thought process. I need an equation that has volume in it. And because it's a floating object problem, what equation jumps out to you that has volume in it?
The buoyant force is equal to the density of the fluid times the volume times the gravity.
Good. So the buoyant force equals density of the fluid times the volume submerged times gravity. Gravity we know. We are trying to solve for the volume submerged. So that's the one variable that should still be left in here, and we should be able to replace everything else. We know because it's in water, the density of the fluid should be 1,000 kilograms per cubic meter, which means all we need left is the buoyant force. And again, I feel stuck. If you feel stuck, go back to your free body diagram and create a net force equation. What forces are acting on the submerged object?
Buoyant force and gravity.
Buoyant force and gravity. And there is one more.
Spring force.
The spring force, which we see is 4.2 newtons. So now I'm going to use that to create a net force equation. Net force.
So the point 0.8.
What's that?
Oh, my mind was just thinking the buoyant force would be 0.8 because that's the difference in the what the spring scale is reading and the.
You're right.
Well,
I'm still going to work through it, but you are absolutely correct.
okay.
So then, as we did before, we're going to fill in our forces. Forces up minus forces down. So buoyant force plus spring force minus the force of gravity equals mass times acceleration. And the acceleration collapses the right side of the equation to 0. With me? So the buoyant force is unknown, but that's what we're trying to solve for, so we can plug it back into that equation. Plus the spring force, which is 4.2 newtons, and the force of gravity, which we already calculated to be 5 newtons, equals 0. And as Olin already pointed out, when you take those two values and combine them and bring them to the right side of the equation, you find 0.8 newtons equals the buoyant force. And it should make sense that it's a positive force, because which way is the buoyant force pushing it?
Up.
Up. Before I finish, do you guys have any questions up to this point?
I think so.
Okay.
I'm good.
So the force of gravity is 5 newtons because that's what the spring scale reads, because that's what's pushing down on the
Yes.
object. Okay.
And if you weren't sure, you could have also plugged in mass times gravity. And you knew the mass was 0.5, and we know gravity is 10, so you're still going to get 5 newtons out of it. Whether you do it mathematically or realize that the spring scale with no other forces acting on it read the weight.
Okay.
Good question. So now we have the buoyant force, which means we can bring this orange, I don't have an orange, this purple equation back in to calculate the volume. So we know 0.8 newtons equals the density of the fluid, which is 1,000, times the volume, times gravity, which is 10. Holy smokes, this is going to be small. So we divide both sides by 1,000, and then we divide it by another 10, or really we can combine those to 10,000. Right?
Yeah.
And 0.8 divided by 10,000. 1, 2, 3, 4, 8 cubic meters equals the volume of the object, aka small. This is brutal, but the more of these problems you do, the better you will get at them. But now we have the volume.
Yay!
Yay! Which means we can divide that out and calculate our really, really high density. Assuming I haven't made any mistakes, you should get 6,250 kilograms per cubic meter. Holy crap, we got the right answer.
I forgot that was what we were looking for.
I'm pretty close with you.
I was like, what are we looking for this for again?
Some of these problems will be long and brutal.
Some of them.
Sorry. But the more you do of them, the faster they get. And when they start to feel monotonous and tedious, that's a good thing. That means you get it.
Cool.
Before I dismiss you, do you have any questions? All right, then I'm going to end the video recording and pray that Camtasia works. Recorder is not responding. I will continue waiting. Take as long as you need, Camtasia.
Oh no.
I thought you deleted it. I was like, Bear, no.
I thought the video was corrupted.